Good time doing the work problems and energy problems last night without any difficulties. Today we move a little bit further into this and take a little deeper look at these things. So again, a quick reminder, a quick review. Work changes the energy of a system. My next question should be is what type of energies can a system possess? And it turns out there's a lot of them. There are many forms of energy, including light energy, acoustic energy, sound has actually got energy involved, nuclear energy, of course, electrical energy, vibrational energy. There's a lot of them, but in this chapter, we're going to focus on just the following basic four types. Gravitational potential energy, the energy due to height, kinetic energy, the energy due to motion, elastic potential energy, the energy stored in a compressed or stretched spring, or rubber band, and heat, which we oftentimes just call energy dissipated. Why don't we just call it just heat? Why do we use the fancy word energy dissipated? Well, sometimes, like for example, when you drop a rock on a tabletop, yeah, all the energy is lost. Some of it gets converted into heat, but some of it gets converted into sound, which bounces around the room quite a bit, eventually turning into heat, but it might be a while. But we'll just call it as energy dissipated. That's energy lost from the system. It's eventually going to be formed into heat, but it may not be heat right away. So we're a little bit more picky in physics. Here's a quick image of what happens. This is supposed to represent like a chunk of metal on the microscopic level. You just dropped a piece of metal onto the tabletop. What's happening? The molecules that make up that particular piece of metal start jostling. And as it hits each time, more and more of the energy is being converted into jostlings of those molecules. In fact, as you watch this thing sort of hit here, in this case it's saying energy E is equal to potential energy, which we're going to represent by a capital U, plus the kinetic energy, which we represent in this class with a capital K. So E energy, U potential energy, K kinetic energy. And in this case, the potential energy due to height, gravitational potential energy, is slowly being converted here into the motions of these molecules. What do we call that particular kind of energy? We're calling it heat or dissipated energy, or that sort of wider term to cover all of those things. So you can sort of see what's happening here. Eventually, all of it gets converted here, and yes, you could even figure out the change in temperature of this piece of metal if you knew how much gravitational potential energy it started with and its mass. You could figure out the change in temperature in the material, of course. So all energy eventually converts to heat. Where does it all come from? The sun, basically, in our case, almost all of these energy we're dealing with. So take a look at these couple of ones. So gravitational potential energy, represented by capital U, which is potential energy, sub G, meaning this is the potential energy due to gravitation or gravity. How much energy does a 5 kilogram mass gain if you lift it 2 meters upward? Well, you can sort of figure it out real quick. Here's our 5 kilogram mass. Force of gravity on it is 49 newtons. And if you lift it up 5 meters, how much energy does it, 2 meters upward? You can sort of see it real quick. This, of course, is equal to mg. And let's just make this all in variables. Well, I guess let's actually solve this one. This would be 49 newtons is the force of gravity. To lift it up at a constant speed, you're going to have to apply a force of 49 newtons this way. So how much work did you just do? To lift this thing up 2 meters at a constant speed, you would have done 49 newtons times 2 meters, that's our displacement, times the cosine of 0 degrees. Or you can say, oh yeah, it's equal to 98 joules. That's how much gravitational potential energy, that's how much work you did, and how much gravitational potential energy that object gained. If you lift that mass up, that 5 kilogram mass up 2 meters, it now has 98 more joules of stored gravitational potential energy than it did when it was on the floor. You can release that energy by just releasing again, and as it falls, it'll convert that into 98 joules of kinetic energy, energy due to motion. And when it hits the floor, it'll convert that kinetic energy into 98 joules of energy dissipated, heat, sound, whatever kind of things, even light. You're like, really? Yeah, light. More general terms, how do we calculate this? Well, we took the force of gravity, which is that, times the height change, which is delta H. And so usually you'll see the change in gravitational potential energy is just equal to mg delta h, the change in height. The units again for this are just force times distance or joules. The one question that we usually run into in this one is, wait a second, where do you set the 0 point for the gravitational potential energy? You're like, oh duh, E, it's the distance to the floor of the room. Well, is that really the 0 point? Well, technically you could go all the way down to the floor outside the building, but is that a good 0 point? You're like, oh no, technically, Concordia is 8 meters above sea level. You should really use sea level. Well, is that really 0? Well, you could go to the bottom of the ocean, but even there you could dig a hole, if you can imagine, all the way to the center of the earth. You're like, aha, that's the 0 point for height. Well, you could remove the earth, and then of course our object would fall all the way to the center of the sun. You could remove the sun, and it would fall all the way to the center of our Milky Way galaxy. You could remove the Milky Way galaxy, and our object would still keep falling all the way to the center of our local group of galaxies, the center of mass of that system. So you're like, wait, what? Where do you set this at? And that's the answer is you can set it anywhere you want. If you're curious, physicists set the absolute 0 point at infinity. You're like, what? Yeah, don't even worry about it. Which is why we usually don't say this is the absolute value of gravitational potential energy. We talk about the change in the potential gravitational potential energy as we lift an object from the floor to a given height. The key on this one is you can use any convenient height as long as for a particular problem you keep it consistent. You can't say, oh, I'm going to make it the floor for this part of the problem, but then I'm going to make it the floor outside the building in the next part of the problem. No, you can't do that. The other thing is, depending on where you set your height, your h equals 0, you can have negative potential energy. So for example, you say, all right, I'm going to set h equals 0 at the side of this tabletop, but now if you drop an object off of it, when it hits down here at the bottom, its delta h is going to be some negative value. It's now at some negative height, which means it has negative GPE. Don't panic, it's actually fine. We're really talking about the change of gravitational potential energy. In this case, the negative number means you lost that much potential energy. You would say, I've got 0 GPE up here, gravitational potential energy, and I have less than I have down here. It's less than 0. I've got negative height. So let me show you some examples of this real quick. Not examples, moving on. The other type of energy I want to talk about real quick is kinetic energy, which we represent with a capital K. The energy of motion, it's equal to 1/2 mv squared. You probably learned that back in middle school. The units for kinetic energy, again, are Newton meters. If you rearrange all this, I could show that it's true that, or joules. So take a quick look at this. Who has more energy? A 50-kilogram athlete running at 10 meters per second, or somebody who's twice as massive who's running at half the speed? And you're like, oh, it's got to be the same. Be careful, because of the squared term, and I'll let you think about for 5, you can pause the video if you need to, 4, 3, 2, 1, 0. Who has more energy? It's the 50-kilogram athlete. Because of this velocity squared, even though this gets half as big for the 50-kilogram athlete, I'm doubling this and then squaring it, which means the 50-kilogram athlete has twice as much energy as the 100-kilogram athlete who's running half as fast. So which one would cause more damage to you, cause more physical damage? The answer is the 50-kilogram athlete running twice as fast will do twice as much damage on you. It's kind of interesting and fun. If you apply a force for 10 newtons for a distance of 2 meters to a 10-kilogram object that's initially at rest, what will be its final velocity? And you might say, oh, okay, I know how to do this one. Use F equals ma, Newton's second law from last chapter. Figure out the acceleration. Once you know the acceleration, you can use, v final squared equals v initial squared plus 2a delta x to figure out the final velocity. And boom, you got it. But there's something amazing going on here. Remember that work is equal to the change in energy of the system. In this case, how much work is being done? Well, 10 newtons for a distance of 20 or 2 meters gives us 20 joules of energy. What type of energy is that being converted into? It's being converted into kinetic energy. So what's the final velocity of our person or object? Well, if you just plug in that 20 and set equal to 1/2 mv squared, you'll end up with, okay, this is 5. Divide both sides by 4, or 5, we get 4 equals v squared. And voila, what's the final velocity of our object? It has to be 2 meters per second. Energy is a lot faster to solving a lot of problems than using forces and accelerations and your kinematic equations. And that's why energy, physicists love energy, physics students love energy as well. So take a look at this next worksheet. Just a little quick practice with gravitational potential energy and kinetic energy. And take a quick look at it. You've got a little person up here. And it says PE, really what it means is gravitational potential energy is 15,000 joules. And the kinetic energy is 0. In other words, they're stationary. As they jump off, their gravitational potential energy gets smaller. Why? Because they have less height. But what has to happen to it? Since energy is conserved and we're not generating any heat, as far as we know, it's being converted into kinetic energy. And so I'm giving you sort of the first one here. This one's 3,750 joules. So the sum of these is still that 15,000 joules that we started out with. What happens when they're midway down? Think about it for a brief moment before you go forward. Half of the energy is gravitational potential energy, 7,500. And the other part, of course, is the kinetic energy. So it's getting larger and larger, getting faster and faster. Down here, the next part, their gravitational potential energy is all the way down to 3,750. Where's their kinetic energy going to be? Well, it's 11,550, sort of the same as this, but now reversed in order. And then finally at the end here, think about it. Just before they hit the bucket, their GPE is 0, their height is 0. What's their kinetic energy just before they hit the bucket? The answer is it's 15,000 joules. Now what happens to all that energy once they hit the bucket? The answer is it gets converted into E dissipated. Heat, sound, splashing, whatever you have, but eventually all 15,000 joules ends up as heat. And a couple of quick other examples here. This one always stumps students, and that's why I wanted to do it with you. In this case, they tell you the velocity in kilometers per hour, yuck, horrible units, and the kinetic energy is 1,000,000 joules. The question is what happens to the kinetic energy if you double the velocity? And a lot of students are like, well, wait, you can't solve it because we don't know the mass. Oh, they're like, okay, let me convert kilometers per hour into meters per second, then I can figure out the mass of the car, and then I can work on this next one. Don't think about it that hard. What's really happening here is I'm doubling the velocity. And if you remember, kinetic energy is 1/2 mv squared. What's going to happen to my kinetic energy? If I double the velocity, it should go up by a factor of 4, or 4 times 10 to the 6, 4 times as much as it was to begin with. What happens if I go up to 90 kilometers per hour? Well, you're like, wait, 60 to 90, that's not nice. Yeah, look at the original one. To go from 30 to 90, I triple the velocity. What's going to happen to kinetic energy if I triple the velocity? Well, 3 times the velocity squared is going to give us 9 times as much kinetic energy. Finally, this last one here, it's a pile driver where they take a big mass, if you've seen these here in Shanghai, and they drop it and actually pound in pilings to support buildings like Concordia is built on. What happens here? It starts out with GPE of 10 to the 4 joules, or 10,000 joules. And the question is, how much work does it do on the piling as it hits? Well, remember, work is equal to the change in energy. The change in energy in this case is, I assume that the final height is going to be 0. I hope, because we have no other information. So how much work is being done? The answer is all 10 to the 4th joules of loss of energy gets equal to the work that's being done on the piling. What I'd like you to try right now, as this video is about to end, is go ahead and try the conceptual worksheet. Looks like this. We've done 3 of the problems on it. Give it a quick try the other ones before you move on with the next series. All right, see you soon.